All right, before we get started on the snow morphology presentation, we are going to begin a supersaturation experiment. It isn't going to be the more complex ones. It's really just going to help to illustrate how crystals form differently depending on what the conditions are, okay? So the first thing is each of you has 100 mils of water next to your hot plate, all right? That is going to be, don't turn it on, don't turn it on. The first thing you're gonna do is you're going to take half a teaspoon of salt and you're going to put it in the water, all right? And you're going to stir it. You're going to stir it until the crystals are gone, okay? Stir it until the crystals are gone. And you're going to stir it until the crystals are gone. Now, once they are gone, if they do get to the point where they get gone completely, then what you're going to do is you're going to take another half teaspoon of salt and you're going to put that in the water and you're going to do it again. And you're going to continue to do it until when you're stirring it, it is going to, not everything's going to dissolve. Okay, the goal is to get this so full of salt that it's not going to dissolve. And we already talked about this in chemistry, and we've talked about this a little bit in dealing with dew point, but now we're going to deal with it in terms of crystals and snow. All right, so you're doing that thing right now. Go ahead and do that. And they would go ahead and do that. All right, everybody's done with that. Take your stirrer out, all right? And I want you to turn your hot plate to 2, all right? Turn your hot plate to 2, and we're just going to let it run. We'll see how far it gets. Again, snow morphology. Remember the Greek word for form is morphe, and then logos just means thing or idea, or actually the most comprehensive idea that Aristotle used it as an idea of something that was representative of reality, okay? So the way the different forms of snow are. All right. We just started that. Now, this is a quartz crystal. Now, again, let's go back to Unit 2. When we talked in Unit 2, we talked about how different minerals are going to form. And when different minerals form, this, for instance, this quartz crystal, does this form quickly or does this form slowly? Exactly. It forms slowly. It has to form slowly in order to form these clear edges. If given enough time, it will form things that is in such a way that it's representative of its actual molecular shape, okay? However, if it's cooled off quickly, then you end up getting obsidian. Remember, obsidian is these atoms are just all smushed together in all sorts of forms because they went in all sorts of like somewhat random forms, because what happens is it cools so fast that they just come and sit next to each other in weird angles, and it's very unpredictable. All right. Now it isn't actually random, but it kind of looks random. And my point in reminding you about this back from Unit 2 is to discuss the fact that crystals form differently dependent upon the conditions. You understand? Crystals form differently depending upon the conditions. It isn't exactly like what we just talked about here, but I want you to use this as a reference point going forward. All right. What causes snow to take various formations? There's a bunch of different things that go into all the different kinds of snow that we've seen before. Temperature is one of them. The air movement is another one. The type of what's called a nucleator, which is the seed, which is the thing that it starts with, which we'll talk a little bit more about in just a bit. And then also the moisture. If the air is really, really full, has a lot more water than it can hold, what's going to happen is you're going to get really big, weird snowflakes. If it's just enough and it's really cold, you're going to get these small, kind of like prickly little snowflakes, right? But we're going to talk about that more in just a second. Nucleator and winter weather. Crystals need a surface to start on. Now, if you ever put an ice tray in a refrigerator, what you're going to end up experiencing is that the ice is going to be along the edge primarily. Now, it's logical that it is because that's kind of where the cold is. But it's also logical because it gives the ice a surface to attach to. Yes, the cold air can't get to the middle, but it isn't necessarily going to form on the top. The top is right away where you're going to get like an ice film across the top, but those edges are where it's going to be the strongest because that is where it has something to attach to. This is an idea of a nucleator. That would be a piece of pollen. All right. Now with that piece of pollen, what happens there is that gives it that kind of rough edge, like the edge of an ice tray, to attach to. And so once weather gets cold enough, what happens is that these frozen little water particles are going to more readily attach to something. If they're still liquid, they can kind of get schmutzy and they aren't necessarily going to attach to one another unless the dew point gets exactly where it should be. But before then, if the dew point doesn't get quite to that point, what's going to happen is that these little pieces of ice are going to crystallize. They're going to start to get hard, and which makes them easier to attach to something. And that's what begins to happen. It starts to attach to a nucleator. Now, this still happens with rain too, but with snow, it becomes more important in some ways because that, based on whatever the nucleator is, that's going to be what kind. Very often, that's going to be what kind of snow you get. This is called the Nakaya diagram. Back in the 1930s, a Japanese physicist named Nakaya, he came up with this pattern. He found this pattern where that if you go from 0 degrees Celsius to -4, what you got were these kind of like simple flat plates. They look simple, but they're not really simple. They're incredibly complex. And then from -4 all the way up to -10, then you're getting these, what they're called prisms, sheaths. It's a number of different things that they can be called. But they start to form, instead of forming out like this, like the plate is, they start to form up like this. And then at -10 to -22, then it starts to form out like this does again. So first it starts to form out like this, and then it starts to form up like this, and then it starts to form out like this, and then once you get down to -22, then it starts to form up like this again. Now, and we'll get into kind of why that is the case. Here's the different styles. Obviously, this is what we're accustomed to when we see snowflakes. Now, what you do see here is that there are these kind of like fine little areas, and then there's like a really fancy little plate in the middle. Here, this one has some kind of fine ends around the edges, and then there are these tiny little plates out around the edge. This one is comprised almost entirely of plates. That's what happens when you have different pressure, different temperature, different amounts of water in the air. All those things are going to occur. Now again, needles, prisms, columns. If you look here, again, the water is frozen on the edge, just like on the ice tree. And then in the middle, it starts to melt a little bit. This is like the sea crystal is way down here. But the first part of this to kind of begin to melt is these edges. And so it forms out these kind of hollow little cones. Sometimes it can freeze again and cap that off and create, there isn't one here, sad. Or you can get needles, and needles are really long versions of that. Capped prisms. With capped prisms, you go back to here, it's like these six-sided items, except what happens is the plate, remember I said that it grows up or it grows out like this? In this situation, it's growing up, and then it gets to a certain temperature, and then it starts to grow out where the water is attached, and the water is attached on the ends. All right? Cover that a little bit more here in just a second. Plates, crystals, and diamond dust, what you find about these is that these are these tiny little things that are way over here on the end of the Nakaya diagram. All right. Real quickly, we're going to talk about basal and prisifacet. Now, I talked about it growing the long way, and I talked about it growing this way like a plate, okay? If you get more technical with that, the idea is that you have the basal facet. The basal facet is when you look down on it, you see the six sides. The prism facet would be like looking at a snowflake from the side. Okay? So this is, if it grows out like this, that's like a regular snowflake that we're accustomed to. Okay? If it grows on the basal facet like this, then what's occurring there is it's making these little prisms. All right, those long things, these. Making these. All right? All right, so an H2O model. I want you to back up a second. We are now going to take these little things. Remember these from chemistry? These are H2O, right? Now, don't worry about the fact that there's different colors. Just think of the little balls on the end, or they're always hydrogen. Like I said, I don't have enough colors. All right, so each of you has that model. What I want you to do is to use these in such a way so as to come up with a hexagon, okay? Simple hexagon. Go ahead and do it. Go ahead and do it. All right, now let's take a look at what you should be seeing. Let this baby run here. There we go. So this is a computer 3D modeling of this. The blue ones, the blue ones are oxygen. The hydrogens are the little pink ones. Now you can see right here, look at that, hexagon. Now I can see some of you have put hydrogens, excuse me, I can see some of you have put hydrogens at the points on the hexagons. I need you to mess with it again to make sure that the oxygens are there. Now look, it's gonna be weird. Some of these are gonna look a little bit weird, but I want you to tinker with it to make sure that there's an oxygen at every point on the hexagon. Go ahead and do that. And then go ahead and do that. All right, next I want you to check the temperature of your water. All right, grab that thermometer, check temperature of your water. We're gonna see how far this goes, all right? Because eventually, here's what we're gonna do. We're gonna take the water in there. We are gonna add more salt once it completely heats. All right, once it gets up to the 50 degrees centigrade like we talked about, it's gonna get up to that temperature. We're gonna add some more salt until it gets full of salt again, until it becomes super saturated. We're gonna put a tiny bit into this one, and we're gonna put it in the desiccator, all right? And then this one, we're gonna pour most of it out, and we're gonna set it over there in the window. Then we're gonna compare the crystals that the two make next week, all right? So moving on, back to the Nikaya diagram. Something I want you to notice. See this little hump here? This little hill? That little hump is the supersaturation angle. That's what I was just talking about. You take the water and you put it in these two different situations, whether you cook it really fast or you just let it dry on its own. It's going to form different crystals, right? And I want you to see the fact that these two different processes are going to form these different crystals. This is the supersaturation line. Now what you can see is that below the supersaturation line, it still forms crystals because like I said, once it gets cold, there are these little ice crystals floating around up there, all right? Now, normally dew point would necessitate it forming with water, right? But instead, in this situation, once it freezes, it can attach to anything. And sometimes it does. And so in these low areas, that's where you get the diamond dust. It's like kind of like painful stuff that when it blows, it kind of smacks your face, right? But then as the air gets more and more water in it, you get these increasingly complex things. Because what happens is that there's more and more water in the air to attach, and then there's more and more water in the air to attach. You get increasingly crazy patterns. So increased humidity causes more complex snowflakes. So lastly, the thing I want to cover is that climate change can have a number of effects on this, all right? One of them is that warmer winters are going to have less and less snow, all right? Now that figures because it's not going to get to freezing, right? But in addition, what you're going to have is back here, it's going to be warmer. And as a result, you're not going to have these super complex things. So the snow cover is going to be different, which is going to affect animal life. It's going to affect plant life. It's going to affect how much water, how well water is dispersed. It's going to affect blowing and drifting snow. A number of different things are going to change as a result of that, all right? So the second thing I want to mention is that less killing cold, since it's going to be not quite so cold, like in this range over here, as a result, because like I said, the majority of the low temperatures are continuing to get higher. It's one of the chief things that the UN had noticed. Less killing cold results in different materials entering the air, all right? So you get more crud in the air, whether it be carbon processes or whatever. And then also warmer water is going to hold more salt. So as a result, the warmer air holds more water. And then also, lastly, there are dangerous pathogens that can be easily transported. They can function basically as nucleators. and as a result, they can end up destroying plants. All right, let's check on your stuff. Let's see where your water's at.